Welcome, everyone. Thanks so much for being here tonight. My name is Megan Nguyen, and I'm the new Community Events Manager at the Peninsula Open Space Trust. And I'm so excited to welcome you to Exploring the Night Sky. Thank you so much for tuning in tonight. We have a superstar speaker that I can't wait to introduce you to. Tonight, we're going to have fun and we will have many chances to ask your cosmic questions. So let's explore the deep depths of the universe together. For those of you who are new to Post Work, we are a nonprofit land trust, and our mission is to protect open spaces on the peninsula and the South Bay for the benefit of all. We are creating a network of protected lands where people and nature connect and thrive. Since 1977, Post has protected over 80,000 acres of land. Thank you to all the donors and community members who have made this work possible. We couldn't have done it without the support you give to us. So thank you. Before we begin, I want to start by sharing the inspiration behind tonight's event. One of my favorite things to do when I go camping is to look up at the night sky and see the stars. And I was recently inspired by the James Webb Telescope images that NASA recently released. You may recognize some of the images that we use in our event flyers and graphics, and also my Zoom background right now. And even though the Bay Area is a busy city place, there are a handful of places where you can go up into the mountains and see the stars on a clear night sky. Naturally, we got curious and called in an expert to help us make sense of the stars, and I'm thrilled to introduce you to our speaker tonight. Samuel Singer is an astronomy educator and founder and executive director of Wyoming Stargazing. He has been recognized by NASA as a volunteer solar system ambassador, as well as by the IGES and NASA in their Top Stars program for an astronomy lesson plan he wrote. In 2013, Samuel completed his doctorate degree in science education from the University of Wyoming. His dissertation research focused on spirituality and outdoor environmental education. And after wrapping up his dissertation, he founded Wyoming Stargazing as a way to further his passion for helping others explore the universe. All right, without further ado, let's have Sam join us. Hey, Sam, how's it going?
I'm great, Megan. Thanks so much for having me. How you doing?
Hey, good to see you. Thank you so much for being here tonight. We're so excited to have you.
No, it's my pleasure. Thanks for having me.
All right. Well, before we dive into the great content that you'll be sharing with us, can you tell us a little bit about yourself? Like, what's your story? How did you get into astronomy?
Great question. When I was about 6 months old, my dad had me out watching a meteor shower. An incredibly huge meteor streaked through the sky, lit up the whole sky like a flare gun. Tiny bits of meteor dust sprinkled down all over the place, and one little speck landed right on the tip of my nose, and I breathed it in.
Whoa.
That was the beginning of how I got into astronomy. That story is not true. What really happened is my dad did take me out to watch meteor showers when I was a kid. We grew up in northern Nevada where the skies were really, really dark. I remember watching Hale-Bopp Comet with him, meteor showers, and just spending time outside, being quiet, looking up. And so I fell in love with the night sky from a young age, and then got really lucky. I was able to take a high school astronomy class in astronomy, and then ended up at a college where there was a young professor who had just arrived the same semester that I had, and he really wanted a protege, and that's who I became. And we built up the astronomy department together, and here I am.
Wow. Well, you definitely got me in that first version of your story. It just seemed like a magical movie action scene. But I mean, like the second story really kind of speaks to your journey in education, which is really interesting. And we're excited to have you teach us a lot today. So thank you so much for sharing that.
Yeah.
Can you tell us a little bit about what you'll talk about today? Give us like a high level overview.
So the highest level overview is we're going to explore the universe. We're going to start really broad with a question. and we'll answer that question to the best of our ability. And that's going to bring up new questions. And so the whole presentation will be driven by all of you out there watching. You can chat your questions, and depending on what you ask, we'll go off in different directions.
All right. Well, you heard it, folks. Sam is ready for your questions. So type away in the chat and we will answer them during the talk. We'll also have time at the end to answer more questions if we don't get to all of them. So definitely keep asking, and in the chat, we'll monitor it and we'll ask while we're going in this presentation. All right. Okay, Sam, why don't you go ahead and launch away? Take it away.
Awesome. Thanks so much, Megan. Well, again, thank you so much for having me here this evening. Before we get into the content of my talk, I'd like to begin with a land and sky acknowledgement. As you'll see later on this evening, the study of the universe is really the study of the past. We look back in time as we look out into the cosmos in order to understand the present conditions that we see. And so we must also look back into our past on Earth and understand and honor those who have come before us. So we acknowledge that we are living, meeting, teaching, learning, and enjoying the night sky as colonizers in the unceded and occupied territory of many indigenous peoples whose past, present, and future generations steward these lands and skies. The current arrangement of the stars into constellations that are drawn from the ancient Greeks, Romans, and as well as from Europeans in South America, are but one of a myriad of arrangements of stars into constellations created by native peoples living in every corner of the globe. Their arrangements of stars into constellations told their own stories and are no less valid than the currently accepted astronomical constellations. We acknowledge their deep connection to this place, including the skies above it, established and passed on through innumerable generations, living and carrying out their hopes, dreams, and their lives on these lands and under these skies from which they were forcibly removed. Their stories of the skies predate ours and contain much wisdom. We offer respect to their elders past, present, and future. We acknowledge the legacy of violence, displacement, migration, and settlement that bring each of us here in the present. And now, with all great acts of learning, we'll begin with a simple question. What would you see if you pointed a camera at the night sky and took a more than 12-day long exposure, focusing in on a tiny, completely dark piece of the sky that you could cover up with a grain of sand held at arm's length? So I'm going to give you a moment to think about that. But before we do that, I want to give you a little background about what I'm talking about. So first, I mentioned a 12-day long exposure time. What is that all about? So with the camera, the longer you hold the shutter of the camera open, the longer light comes in. So here are a couple examples. These are two pictures that I took a couple of weeks ago when the moon was full. One exposure was only 1/1500th of a second, and the other was 1/150th of a second. And you can see that longer time of the exposure had more light coming in. So we're talking about not a second, not even a minute or a day, but 12 days of exposure time. And this is a very special camera. It can cancel out daylight, clouds, all that. It can stare at this tiny little piece of the dark sky without interruptions for 12 days straight. So what are the options? Maybe the tiny piece of dark sky is actually dark. We don't see anything with our eyes, and neither will this camera. It's just going to be total blackness. At the other extreme, maybe there's so much light from stars, galaxies, refracted off of dust, that after 12 days, it's going to be completely overexposed, and all we'll see is white. So what do you think? What are you going to get when you take this 12-day long exposure? Got some great questions coming in already, and it's wonderful. But I'm so curious about what you think about this image. What do you think you're going to see? Sarah Tang says perhaps it would be overexposed. Certainly a possibility. There are a whole lot of stars out there. Any other guesses? Completely white from Lillian Lilypad. Aerospike 00 says that's a lot of photons you would be capturing. Indeed it is. Photons are streaming everywhere in the universe all the time. Let's take one more, and then we will reveal what this image actually is, because it's been done. Here's one from Will Balson. If it's a visible light camera, then probably you would see a whole lot of galaxies. Well, you happen to be correct. So here it is, a tiny piece of the sky that you could cover up with a grain of sand held at arm's length. This, as you may know, is the deepest image of space ever taken, and it was the first image released from the James Webb Space Telescope, and it was Megan's background image on her Zoom screen as well. Nice choice, Megan. So this is Galaxy Cluster SMACS 0723, and it's teeming with thousands and thousands of galaxies. By the way, SMACS stands for Southern Massive Cluster Survey. Just one of the many acronyms that astronomers use to group different research projects and objects into categories to make it a little bit easier to understand. The southern part is because this object is actually in the southern sky. It's in the constellation Volans. And so we can't see it in the northern hemisphere. But as you may know, the James Webb Space Telescope is out in space. And it's at a location where it can look stuff in the northern hemisphere, southern hemisphere, or anywhere in between. So great question. The significance of the 12-day long exposure from Maya SH-R. So that's how long the camera, the near infrared camera to be specific, on the James Webb Space Telescope used to capture light from this area of the sky. It didn't do it in just one 12-day go. It took several images over hours, and then they were all digitally stacked together to accumulate 12 days of exposure time. But this is just the beginning. The James Webb Telescope is going to take longer exposures. So we'll be able to see even deeper into space as those pictures come out. And so this picture right here, the objects in the center, which are kind of all warped and weird looking, represent a foreground galaxy cluster. That's actually closer to us than a lot of the other stuff in the image. That close galaxy cluster is about 4.25 billion light years away. So what that means is the light coming from that object took 4.25 billion years to reach us. So we're seeing it as it existed 4.25 billion years ago, which is roughly the time that the Earth was forming around the sun. So we are looking at ancient light. That's what I was referring to back in my intro about looking back in time. We're literally seeing how the universe was 4.25 billion years ago. The warping that I mentioned is called a gravitational lens. And that's caused by the gravitational effect of that galaxy cluster in the center of the image itself. So I've got literally about 100 slides of information to share with you about this image and related topics. But here is where you get to take the reins. I want to know what you want to know about this image. When the Hubble Space Telescope first took the Hubble Deep Field 30 years ago, my astronomy professor told me that he just stared at it for an hour just to try to absorb it all. So I want to give you a minute just to stare at this and see what questions pop up for you. We can tackle pretty much everything in the universe. So I want to give you a moment and yeah, post your questions and we'll take it from there. Ashiana asks, how do we know anything about what's beyond the observable universe, if there is anything at all? Oh, fantastic question. So there is the universe, which by definition is everything. And then there's the observable universe, which is the part that we can actually see. The reason there's a distinction between the entire universe and the observable universe is because light has a finite speed. It's not infinite. It's really, really fast, about 3 times 6,000 meters per second, excuse me, or 186,000 miles per second. And so because the speed is finite, it takes light a certain amount of time to travel from one object to another object. The other piece is that the universe actually, at least we think, has a beginning, which took place about 13.84 billion years ago. So for roughly 13.5 billion years, light has been streaming through the universe. And because the speed of light is the fastest speed there is, that light could have traveled a maximum distance of about 13.84 billion light years. Anything that has expanded farther away from where we are right now in the universe hasn't had time for its light to reach us. So the universe has been expanding for 13.84 billion years. Light has had that long of a time to travel. So that's the extent that we can see of the universe. 13.84 billion light years in every direction. Now, well, if the speed of light is the fastest speed there is, then how could the universe be bigger than that? Well, space-time itself doesn't have that same restriction of how fast it can expand. There was a time when the universe was expanding much, much faster than the speed of light. So we believe that the entire universe is probably 90 billion light years across, maybe more, maybe less, but we can only see about 13.84 of it. In time, we'll see more. In another billion years, we'll be able to see 14.84 billion light years in every direction, and so on and so forth. Fantastic question.
Sam.
Yeah, Megan, go for it.
Yeah, we have a few questions that I'm going to group together. We have questions about what is the big star in the center.
Oh,
and
great question.
You could also talk about the colors and the light we see. Are those real? What do they mean? And also, is each item or light in the photo a separate galaxy? Like, what are we looking at here?
Fantastic questions, everybody. I love it. I love it. Keep it coming. Okay, so the colors, the big star in the center, and all the different little pinpricks of light that we're seeing. So almost everything that you're seeing in this image, every little glob of light is a separate galaxy, with the exception of the little points of light that have spokes coming off of them. The little points of light that have spokes are actually foreground stars within the Milky Way galaxy. So those are the closest objects to us. And those stars are only tens of thousands of light years away. They're our next door neighbors, just within the Milky Way. Everything else, every weird shaped blob, regardless of its color or its size, is a completely separate galaxy to our own. And I want to bring up a couple slides to tell you a little bit more about that and about the colors that we see. I mentioned the James Webb Space Telescope earlier that took this image. Just gives you an idea of how big it is compared to the Hubble Space Telescope, which was huge in itself. And it's much, much farther away than Hubble. Hubble was just going around the Earth at a low Earth orbit. The James Webb Space Telescope is over 1 million miles away. And we'll skip this slide for now. So here's one of the reasons why we're seeing different colors in all these different galaxies. One of the reasons why we see different colors is caused by the composition of the galaxies. Some galaxies have a lot more dust than other galaxies. Some galaxies have a lot more areas where stars are being formed compared to other galaxies, and different amounts of different elements. And so depending on what all that combines to be, we can see different colors. So for instance, some galaxies that you may have seen pictures of appear really blue. They have these amazing kind of blue blobs all through the spiral arms. Those are star-forming regions. Other older galaxies, like elliptical galaxies that don't have spiral arms, appear more kind of dingy yellow or orange. That's because they no longer have the process of star formation taking place to the extent compared to spiral galaxies. What they have is a lot of leftover exploded star stuff, dust, and that refracts red, orange, and yellow light. So they take on that color. But that's not the entire story. And it's not just composition that explains all the color that we see. There's some more exciting stuff taking place. Is this an emission or an absorption spectrum? You are looking at an emission spectrum. That's what those elements where those spikes are the elements present in this particular galaxy that's shown here that are actually being emitted. Great question. And an absorption spectrum would have dark lines in a full band of color, which I'll show you actually in a little bit. So fantastic question. Thanks for that. So here's the other really interesting piece about this image that really blew everybody away. I called it the deepest image of space ever taken, and it really is. We can see stuff farther away than we have ever seen before. There's an object over 13 billion light years away in this image, 13.1, I believe. That little tiny red dot on the bottom of that middle window there. The reason that object is red, appears red, doesn't have anything to do with its composition. It's not dust. It's not star-forming regions. It has to do with what is called redshift. Redshift is the stretching of wavelengths of light due to the expansion of space itself. And I'll go through a few slides, and maybe we'll come back to these ones in a minute, but I want to get to the spectrum stuff to show you that. We'll come back to these galaxy images as well. Okay, so just to get everybody on the same page, the electromagnetic spectrum has lots of different wavelengths and frequencies of light. We normally think about light as just visible light, but every star in the universe shines in the full electromagnetic spectrum, everything from radio waves to gamma rays. And depending on the intensity of the star or the intensity of an event, like an exploding star, we see different amounts of radiation from different parts of the spectrum. So this gives you an idea of how big we're talking about in terms of wavelengths or how small. and how fast the frequencies are. I also mentioned visible light. It's just a tiny, tiny little piece of the electromagnetic spectrum. So all we can see of the universe with our eyes fits into this tiny little sliver here between ultraviolet, UV, and infrared. The James Webb Space Telescope is focused in infrared observations, and that's actually why it can see so deep into space. Infrared light allows you to see through big dust clouds that are out there. Great question. How can you tell how far away the galaxies are? So that is where we're going with Redshift. So all these wavelengths of light, the color spectrum, has a very specific wavelength or frequency when the source isn't moving. But if the source of light is moving, its color actually changes. The wavelength gets stretched out into a different part of the spectrum, so that if you started with ultraviolet light, over the course of the 13.84 billion years of the expansion of the universe, that light would now appear to us as infrared. And so on and so forth with all the different areas of the electromagnetic spectrum. Space is expanding so much that literally the light that was emitted from a long time ago has stretched out into different wavelengths. You may have heard of the cosmic microwave background radiation. That's the radiation left over from the Big Bang, about 300,000 years after the Big Bang, to be precise. It's the first time that light decoupled from matter, and there was actually electromagnetic radiation in the universe. We can still see that light today. It started in the visible end of the spectrum, but it's been stretched so much that it's now microwaves. And you may have heard that before there was satellite TV, when there were nothing playing on certain stations, there was that white and black fuzz on TV screens. Something like 3 or 4% of that fuzz is actually the cosmic microwave background radiation. So lots of cool stuff. Stephen Garland asks, the objects which we can observe at the edge of the universe, are they fundamentally different from the objects that are much closer to us? Steve, that is the question that the James Webb Telescope is trying to answer for us. How have galaxies evolved over time? We know basically that stars were the same back then as they are now. They're huge balls of hydrogen, technically plasma, not gas, that confuse heavier elements in their cores. Fundamentally, that hasn't changed, but maybe the size of stars on average has changed. Maybe the way galaxies first evolved 12 billion years ago is different than the way galaxies are evolving today. These are the specific questions about how the universe changes over time that we haven't been able to answer yet, because we just haven't been able to look back far enough. So now that we're exploring these objects on the edge of the visible universe, we're going to start to be able to answer some of those questions. How would you define the edge of the universe? Well, depends on who you're talking to. There are some astronomers who would say that it's ridiculous to talk about a real edge. There is no edge. So I use the word edge lightly. So what we think we have is it's a very cool infographic. You have to thank NASA for that. What we have probably is a 3D that is expanding into a 4th dimension. So imagine that you are a tiny, tiny little creature, an ant, and your world seems to be flat. You can walk straight towards something or away from it, to the left or to the right, but it seems like wherever you go, you're walking on a flat surface. But you get this crazy idea one day that if you kept walking in one direction, eventually you would end up where you started. And all your little ant friends think that you're absolutely crazy. You're going to walk off into the distance and they're never going to see you again. But you decide to try. And you walk off in one direction, you just keep walking, and lo and behold, years later, you end up right where you started. You walked in a straight line on a two-dimensional surface, but you were wrapped around a third dimension. So we know that the Earth is spherical, but we walk on the Earth kind of on like a two-dimensional surface, but we know it's wrapped around a three-dimensional Earth. We think the universe is a three-dimensional universe wrapped around a fourth dimension. So if you flew off in one direction, and if you could fly fast enough, actually faster than the expansion of the universe, which is probably impossible, but if you could, you would end up where you started. We think. That does depend largely on the overall geometry of the universe. The jury is still out about exactly what that is, but that's the best answer I can give you tonight. There probably is no edge. We're probably a three-dimensional universe expanding into a fourth dimension. Einstein called that a three-sphere, and he's been right about a lot of other things, so I'll take his word for it. I want to go back to show you those galaxy pictures, because we talked about this amazing image of galaxies, but I haven't really told you what it is and where we are in our galaxy. So let me see if I can get back to those really quick here. Okay, here we go. So here's the Milky Way. This is probably my favorite picture of the Milky Way galaxy. And it's not a real picture, of course, because we're inside the Milky Way. We can't get outside the Milky Way to take a picture of it. So this is a digital rendering of what we think the Milky Way would look like if we could get outside of it, based on scientific observations of everything we can see from within the Milky Way. And by the way, this was put together by one of my colleagues, Robert Hurt. So kudos to you, Robert, for putting this image together. So it shows you the amazing spiral arms of the Milky Way galaxy and where our sun is, out on the Orion spur, not even in one of the main spiral arms of the Milky Way, out in the backwaters of the Milky Way. But that's where our sun is. And of course, we are orbiting around the sun. Here's a lovely profile image of the Milky Way. So you can see that it really is a pancake shape. It's a typical pancake-shaped spiral galaxy with a central bar. That's a more recent discovery, that our galaxy is a spiral galaxy with a central bar. Probably around 400 billion stars, which puts it above average. In that the average number of stars in each galaxy in the universe is about 200 billion. So we have 2 times as many. Lots of different types of galaxies in the universe. Ours is right there in the center, and you can see there's some galaxies that are quite a bit larger in the Milky Way, others that are smaller, all kinds of interesting shapes and arrangements of stars. A lot of the different arrangements of shapes and orientations of stars is due to the evolution of those galaxies. It's now believed that spiral galaxies evolved through interacting with one another, eventually distorting and disrupting their spiral arms to eventually become an elliptical galaxy, a big hornet's nest full of stars. What is in the center of the Milky Way? Asks Ashana. Great question. The same thing that we believe to be in the center of every galaxy in the universe, which is a supermassive black hole. Ours is, I think, only about 4 million solar masses. That makes it a small supermassive black hole. The really big ones, like with M87, actually shown in this image, the big fuzzy white blob, we're talking about 4 billion suns, the mass of 4 billion suns. Great question from Pavan. How do black holes work? Are they just black holes? If you fell into one, would you just continue to fall forever? Great question. So a black hole is a physical object in space. And I'm going to see if I can bring up an image of a black hole here for you. I know I've got one at the very end of my presentation here. We'll go back, but it's really cool to see this. Almost there. Must be a way to get to this without going through all these. Oh, there we go. Okay, so this is an actual image of the radiation around a black hole. What we're seeing here is the galaxy that I just mentioned, M87, and the accretion disk of heated matter that is falling into the central supermassive black hole around that galaxy. So this was the first observational evidence that black holes actually exist. We were pretty sure they existed, but a few years ago, this image came out, and now we know with absolute certainty. So they really are a physical object in space that is so dense that the escape velocity is over the speed of light. So on Earth, we have an escape velocity that every rocket has to surpass in order to leave the Earth's gravitational field. And that's something like 7,000 miles an hour. On a black hole, the escape velocity exceeds that of the speed of light. So not even light can escape the gravitational field of a black hole. That's why they're black. No matter how fast you go, once you're inside the gravitational well of a black hole, there's no coming back. And there is a specific edge, not literally anything demarcating it in space, but a boundary called the event horizon. Once you get closer to the center of a black hole, beyond the event horizon, that's when the escape velocity becomes greater than the speed of light, and there's no coming out. So what would happen if you fell into a black hole? Stephen Hawking defined that as spaghettification. That truly is the astronomical term. The reason you get spaghettified when you fall into a black hole is because of tidal forces. The gravitational pull on your feet, if you were falling feet first, would be stronger than the gravitational field felt by the top part of your body. And so you would be stretched out as you fell inwards. It would not be a good way to go. Spaghettification is what happens when you fall into a black hole. It turns out that the bigger the black hole, the less spaghettification. So if you were to fall into a black hole, fall into a really, really big one, like around M87, in the center of M87, as opposed to the one in the center of our galaxy. You would fare much better with that one. Great question about black holes. Oh, great question from Amit Saini. Thank you so much. Why is the Milky Way in the shape of a spiral? That is a fantastic question. There is no one who really understands why galaxies have spiral shapes. I know that seems strange, given that we know so much about the universe. We don't really understand why spiral structures form in galaxies. What we do know is that the shape of a spiral is ubiquitous at all different spatial dimensions in the universe. At the largest spatial dimensions, we see spirals in the shape of galaxies. We also see spirals form in hurricanes on Earth, on ice caps on Mars. We see them with the fern fronds There's a wonderful vegetable called the Romanesco that also has spiral shapes in it. There are even viruses that have a spiral shape. We don't know why these spiral shapes form, but we see them everywhere we look. That sounds like a good dissertation question for the person who just asked that question. Good luck with that one. You can come up with that answer. You're getting somewhere. All right. So I brought you through these galaxy questions, or slides rather. I mentioned that there are, on average, 200 billion stars in each galaxy. And I also mentioned that there had been previous deep fields taken with other telescopes, the Hubble Space Telescope, for instance. And astronomers have now tried to take these deep space images in lots of different directions in the night sky, but both in the southern hemisphere and in the northern hemisphere. And what they see is roughly the same. They see countless galaxies, thousands of galaxies in every tiny little piece of the sky that you could cover up by a grain of sand held at arm's length. And so you can do the math. You can add up how many little grains of sand could cover up the entire night sky. And you can take the average number of galaxies you find in each one of those little images, and you come up with about 1 trillion galaxies. Then, if you multiply that number by the average number of stars in each galaxy, 200 billion, you arrive at this number for the number of stars in the universe. 200 sextillion. That's a 2 with 23 zeros after it. That's the best guess of the number of stars that astronomers think exist in the universe. 200 sextillion. So there are a lot of stars out there. So yeah, we live, orbiting around just one of them in a galaxy of 400 billion of them. So there's a whole lot of space still out there to explore. I see some other questions that have come through. Great questions about the rotation of galaxies, different sizes of black holes. Can answer a couple of those. So there are lots of different sizes of black holes. I'll take us back to that previous image of a black hole. So the supermassive ones are the ones that are in the center of galaxies. If we could get really close to a black hole, we would see something like this. Once our technology gets good enough, we'll actually start taking pictures of black holes that look just like this. Right now, this is as good as our technology can do. But in time, we will get images just like this. You may recognize this. The movie Interstellar did a great job of depicting black holes as they actually are. So this is that big accretion disk that I was telling you about, where superheated matter is spiraling around the black hole before it finally falls into it. So really big black holes. Gravity tractors. I love it. Yes, they are gravity tractors, and they come in all different shapes and sizes, just like tractors do. Thank you, Henry. Henry's just 10. I love that analogy. Gravity tractors. Henry, with your permission, I'm going to use that on my next presentation. Thanks for that. So the really big ones are at the center of galaxies. We also can get black holes from individual stars. Sometimes two stars that are really, really close together actually share material with each other. One star sucking material off another. And if that one star that's sucking material keeps doing that and gets too much matter around its core, it will collapse inward to become a stellar black hole, or a stellar mass black hole, just 50 to 100 times the mass of a sun-like star, as opposed to millions or billions of times like supermassive black holes in the center of galaxies. So you have your stellar mass black holes, which are 50 to 100 times the size of the sun. And then you've got your supermassive black holes that are millions or billions of times the size of the sun. Astronomers haven't actually found any black holes between those two sizes. They're called intermediate size black holes, but they don't seem to exist. It's a big conundrum. Another great dissertation topic, maybe for Henry out there. Good luck with that one, Henry. If you can find some intermediate black holes, it'll be pretty cool. So those are a couple of ways that black holes can form. There is another way, which is the explosion of a really, really large star. Stars like our sun can't do that. But stars that are at least 8 times the mass of our sun will end their existence violently by exploding in what we call a supernova. And when they do that, their central core will collapse into one of two things, either a neutron star or a black hole. And depending on the size of the star before it exploded will determine whether it collapses into a neutron star or a black hole. But that's the third way that you can end up with a stellar mass. A second way you can end up with a stellar mass black hole. We're not totally sure how the supermassive black holes form at the center of galaxies. They were either potentially lots of intermediate black holes that all came together, and then the galaxy formed around that supermassive black hole, or there were lots and lots of stars that were clumping together, and a lot of the stars fell in towards the center because of gravity. And that's what formed the supermassive black hole. But it's kind of a chicken and the egg question. We don't really know what came first, supermassive galaxies or supermassive black holes. That's another topic that the James Webb Telescope will help to define. Hey there, Megan.
Hey, Sam. We have so many great questions coming in the chat, but I wanted to just take this moment to ask you if there's something you really want to tell us about before we dive into like rapid fire questions.
Yeah, that sounds great. There are a couple quick things that I would love to share with everybody.
Sounds good.
Thanks so much for keeping me on time here. As you can tell, I can talk about this stuff for eons.
I think we're all right there with you. Just lost, and just my mind is blown with all the cool facts that you're telling us. So yeah, keep going.
We'll get some more of that stuff in the rapid fire. But yeah, I want to bring this back home for everybody. So a lot of you are in the Bay Area or in other areas where there's a lot of light pollution. That doesn't mean that you can't do cool astronomy right from your backyard, even if you're in a really big city. So I want to give you some suggestions of what you can do. So the first thing is you can get one of these amazing free planetarium apps on your smartphone or tablet. 2 of my favorites are Starwalk, that I've got pictured right here. Starwalk 1 is my favorite, not Starwalk 2. And then there's also Stellarium. It's both of those are a great way to just get outside. You can just hold the phone up above your head and move it around, and it'll show you all the constellations that are up there and deep space objects, et cetera, et cetera. So those are a great way to get out there and learn about the night sky. Also, Jupiter is up right now. So if you go outside, and you'll see this up in the night sky. Not really. This is a Jupiter image taken with the James Webb Space Telescope. And check out the aurora you can see in the northern and southern hemispheres of Jupiter. Jupiter has northern lights, similar to the way Earth does. What you'll actually see if you go out and look for Jupiter, look to the east right after the sun sets, and you will see this little point of light up above the horizon. It'll be the brightest point of light out there, except if there's a plane going by, but Jupiter won't be moving. Just looking at it with the naked eye, you'll just see this point of light. If you take out a pair of binoculars, you'll be able to see the 4 largest moons of Jupiter, which I did and just held up my smartphone right to the back of a pair of binoculars to take that picture. Io, Callisto, Ganymede, and Europa. You can see all 4 of them there. And then with my 8-inch telescope, oh yeah, somebody else just saw Jupiter. It is amazingly cool. And then I used a telescope with an 8-inch mirror and my smartphone to take this picture of Jupiter. And you can actually see the cloud bands on it. Not quite as good as the James Webb Space Telescope, but hey, not bad for a 10-inch telescope in my backyard. Oh, why does it look blue in the James Webb Space Telescope image? So this is an infrared light image of Jupiter. And I meant to mention this earlier. So all of the color that you see in the images of the James Webb Space Telescope are not true color, because James Webb is not looking at visible light. It's actually looking in the infrared spectrum. But just like with the visible spectrum, there are some wavelengths that are longer than others. And so the scientists working on James Webb code each wavelength corresponding to a visible color that we can see. And when they put those together, that's what we get with all these images. So you wouldn't actually see this if you went out to Jupiter. But snakes, for instance, see in the infrared. So if a snake could see this zoomed in picture of Jupiter, or if we ever launched snakes into space, we had snakes on a plane, right? If we ever launched snakes into space, they will see Jupiter just like this in the infrared. Okay, another cool thing for us folks living by the coast to go out and see, the green flash of the sun. This is real. I've been living out in Half Moon Bay for the past year, and I actually have seen it twice in the last year. The deal is you need a clear, stable atmosphere, preferably no clouds, and a really good view of the horizon, which is why the coast is such a great time to see the green flash of the sun. You want to go out there just as the sun is setting. Don't look directly at the sun until it's just at the horizon. But then, because of mirage, the effect of mirage, and of the different layers of the atmosphere right at the horizon that are different densities, you get a distorted image of the sun. All the other colors get diffracted away from you, just like how a prism diffracts light, splits light into its different wavelengths. The atmosphere works like a prism. The red light and orange light and yellow light get bent away by water vapor. The blue and the purple get scattered by the gases in the atmosphere, and what's left is green. And sometimes when the conditions are just right, you get a little flash of green just above the setting sun. This is actually a picture of the setting sun up above a cloud bank seen from a mountaintop. So you don't have to be at the coast to see this, but it's easiest to see at the coast. So before I bid you adieu with the setting sun and get to the rapid fire questions, let me say happy upcoming cross quarter day. So what is a cross quarter day? Well, you probably know that ancient peoples kept track of the seasons by building enormous stone structures like this one, the Pyramid of the Sun in Teotihuacan, just north of Mexico City in Mexico. And they use these structures to make careful observations of the times where the sun would set and rise in different times of the year, just like with Stonehenge and other areas all over the world. So the cross quarter days happen in between the solstices and the equinoxes. Between each solstice and equinox, there's a midpoint. Those are the cross quarter days. And the ancients actually used to celebrate the cross quarter days as the beginning and ending of seasons. So we're going to play a little name that cross quarter day. Here we go. The one coming up right now is called Samhain. It's going to be in 2 weeks, October 31st and November 1st. We know it today as Dia de los Muertos or Halloween. The following is going to be Imbolc, which we know today as Groundhog's Day, February 1st or 2nd. There's also Beltane, which is May Day, May 1st, and the least well commonly known, Lammas or Loaf Mass Day, as we commonly know it, or I can never pronounce this right. Pardon me. La'ansa, or I think I'm butchering that. But for those of you out there who know how to pronounce it better, you can spread the word on that. But these are the cross-quarter days, the days that fall between the solstices and the equinoxes. So the one that's coming up is Samhain. It was believed to be a time when the veil between the earthly plane and that world was the thinnest, in conjunction with the ethereal curtain changing as the days grew shorter and the nights longer. The idea being that those two realms could cross over and the spirits could easily pass over and walk among the living. Today, we practice Samhain a little bit differently in the United States and in Mexico. Now, the two holidays of Halloween and Dia de los Muertos evolved independently of one another, but they both have commonalities based on the ancient celebration of Samhain. Now, in the United States, we've kind of focused on the ghoulish, haunted aspect of this idea of the dead passing over into the life of the living. Whereas in Mexico, Dia de los Muertos is more focused on honoring those who have passed. So in about 10 days, whether you're celebrating Dia de los Muertos or Halloween or both, I encourage you to look up into the night sky after seeing a green flash at sunset, of course. Grab your cell phones for the planetarium apps and a pair of binoculars and check out the moons of Jupiter. But then after you've done that, put all that stuff aside, look up, find a little dark patch of the sky, and imagine a tiny little piece that you could cover up by a grain of sand held at arm's length. And just stop for a moment and enjoy the quiet of the night sky and imagine what's out there. Thanks so much.
Wow. Can everybody at home, can we just give a round of applause to Sam, please, for such a wonderful presentation. I learned so much, and I have yet to see that green flash, but I'm definitely on the lookout for that because I have heard about it, and I was like, there's no way. But, you know, it's just one of those mysterious things that we're always on the hunt to learn more about. So you're getting so much love in the chat. So I know we're going to go a little over, but let's do our best to just wrap up with some rapid fire questions, answer as quickly as possible, and then we'll do some wrap up announcements. Okay, Sam, what is your favorite galaxy or constellation?
Oh, definitely favorite constellation is Orion because Betelgeuse is in Orion. Betelgeuse is a supermassive star that's about to explode.
Awesome. Okay, what is like your favorite cosmic event, like a meteor shower, passing comet that we need to know about?
Perseid meteor shower, August of every year is by far the best meteor shower of the year. You got to check out the Perseids.
Gotcha. Okay, what would be worse, being sucked into a black hole or being thrown into the sun?
Going into a black hole would be way worse. It would be way more slow and painful.
Yeah, definitely don't want that.
The sun would be over really fast with the sun.
Yeah, we're flashing some awesome comments that are coming in. Okay, do you believe in aliens? Big question here.
Oh yeah, of course. Yeah, so remember, 200 sextillion stars out there. There could be life on planets orbiting each and every one of those stars. There's a whole lot of life out there.
Wow. Okay. Any advice you have for someone who's like super curious and interested in like pursuing astronomy education and learning more?
Yeah, I mean, you just got to get out there. Just go to the darkest place you can find. You mentioned, driving up into the mountains. If you're in California, out by La Honda, there's some amazingly dark places out by Carmel, and just spend some time looking up and enjoying what you see.
Nice. Do you have any recommendations on like a beginner telescope for people to observe? or can we use? What can we use that are easily
Yeah.
accessible?
So Dobsonian telescopes are by far the most cost-effective and user-friendly telescopes you can find. You can get a Dobsonian telescope with a 6-inch mirror for around $300. But a good pair of binoculars that you can buy for like $100, you can actually see the moons of Jupiter through. So you don't even need a big telescope. Like a pair of binoculars will work.
All right, you hear it here, folks. You just need a pair of binoculars. Just get out there and look up and see what you can see. I saw someone in the chat ask about some places in the Bay Area to look at stars. Grant Ranch near San Jose is actually a great place where you can go. You can also even camp there, and that's what we would recommend. Sam, you might have told us that there's an exciting announcement that you want to make, or anything you want to share with us as a closing.
Wyoming Stargazing, the nonprofit that I run, is actually going to start offering stargazing programs in California this coming winter. The details haven't been released yet, but you can check back on our website in the upcoming months. Sometime after the first of the year, there are going to be some opportunities to do some stargazing with us in California. So check back there after the first of the year. And I'd love to take you out stargazing.
All right, everybody, we just dropped the link on the screen here, wyomingstargazing.org. If you want to follow Sam and his work and hear it first about that announcement when we're coming to the Bay. So, Sam, I hope that one day we can go stargazing together. I would love.
We're going to make that happen. Yeah.
Maybe we'll brainstorm some sort of event where we can bring out the community and go stargazing together.
Yeah, let's do it.
All right, one more round of applause. Thank you so much, Sam. You definitely blew my mind.
Thanks for all of your great questions out there. That was a lot of fun. Thank you so much for all that. And again, Megan, thanks for having me here. It's been a blast. And look forward to next time.
All right. Well, if you liked this event, you might like our next event, which is going to be on the earthquake science of the Bay Area and how to prepare for them. That's going to be next month on Thursday, November 17th at 7 p.m. Save the date, mark your calendars. The website registration is available on our website at openspacetrust.org/events. So you can RSVP and never miss our event. And if you like this event, let us know. We want to hear your feedback so we can improve, we can bring new speakers, and you can scan this code with your phone, and it'll take you to a short survey. Your input helps us make better events. So we love to hear from you. Once again, 2 reminders, November 17th, 7 p.m., Earthquake Science of the Bay Area, and please give us your feedback. Okay. Good night, everybody. Thanks again, Sam, and we'll see you next time, everybody.
Bye, everybody.
Bye.